Hello everyone, this is Team 1 progress presentation on constraint covariance theorem based tube MPPI. So controlling an autonomous system can be approached as a finite horizon stochastic trajectory optimization problem. There are many approaches, including nonlinear programming, which heavily relies on initial guess, dynamic programming, which struggles under constraints, covariance theorem, which doesn't scale well due to the enormous number of decision variables. And the paper we chose for the project provides a novel control approach for stochastic linear systems with a non-convex safe space. It leverages both the good points of MPPI and CCS. MPPI is used to generate a reference trajectory. CCS generates a control policy satisfying the safety constraints, and where naive MPPI may lack the robustness and safety due incorrect tuning and tuning, CCS procedure makes this process less time consuming. Let's go to paper and code analysis. So combined approach presented in the paper can be split into three main groups: MPPI algorithm, half space generation, and CCS algorithm. So MPPI algorithm is sampling-based model predictive control algorithm. It starts by taking k-samples of control sequences from Gaussian distribution, then performs a rollout, its forward simulation of our dynamics of the given sequence, and obtains trajectories. Then each sequence is weighted by an exponential transform, and the resulting control sequence is found as a weighted sum. These steps allow us to favor control sequences with higher cost more, and horizon t and number of samples k are hyperparameters that should be tuned per task. Then we go to half-space generation. The constraints in the paper are represented via circles defined by the point and the radius. This step is the proper preprocessing stage where we take first t states of resulting MPPI rollout and project position vectors to each obstacle. After that, we obtain a list of linear constraints used to avoid obstacles. Then we go to constraint covariance theorem. In this step, we use a smart way to merge the resulting trajectory from MPPI, ensuring safety constraints. We want our resulting control sequence to look as much as possible like proposed MPPI, but satisfying constraints. This is done by minimizing the deviation of our distribution. As a result, we obtain a QP problem, which provides us a control sequence. This is our reminder of our improvement plan. So as we said in previous presentation, we aim to integrate pure pursuit and Stanley control as analytical approaches to existing method and deploy all of it in car environment. Let's go to our progress. So we start by analyzing our repository, which was provided with this paper. This repository contains 3 different MPPI implementations with different parallelizations. One is naive, one is threaded, and one is for process parallelization. As we said previously, constraints are defined as circles with point and radius. And we spent some time to discover how we can adopt this procedure to the real racing track. Also, we paid attention to how cost is defined in all components, and we found that we can insert values from pure pursuit and Stanley control into cost of MPPI and CCS algorithm. We will talk about each of these parts later. So let's go to track creation analysis. Taking into consideration how constraints are represented in the original approach, we were seeking for the way to create various racing tracks and use it for evaluation and testing. Our proposed approach is the following. User provides a set of waypoints, roughly describing the flow of the racing track. Then we generate a convex hull and smooth the resulting trajectory. Then left and right boundaries are generated with offsetting along normal of the racing track by given width. Then obstacles are created with a given step along each boundary. At the end, we obtain a unique racing track, which can be substituted to our algorithm directly.
So now let's talk about per pursuit and standing control. So basically, per pursuit is a path tracking algorithm which computes the angular velocity command that moves the vehicle from its current position to reach some look-ahead point in front of it. So we assume that the linear velocity is constant, so hence the linear velocity of the vehicle can be changed at any point. The following algorithm then moves the look-ahead point on the path based on the current position of the vehicle until the last point of the path. You can think of it as a vehicle constantly chasing a point in front of it. So on the other hand, we have Stanley control, which is a similar path tracking algorithm to per pursuit, but while per pursuit uses the rear axle of the vehicle as its reference point, Stanley control uses the front axle, allowing it to directly align the vehicle's heading with the path more effectively, specifically during sharp turns. Stanley control looks at both the heading error and cross-track error, unlike per pursuit that focus only on the former error. To be clear, uh, cross-track error is defined as the distance between the closest point on the path with the front axle of the vehicle. And let's talk about some formulations that we add for integration of these two approaches for our model. So NPPI and CCS cost can be modified by evaluating the desired yaw angle from both per pursuit and Stanley control algorithms by introducing a new yaw penalty term. So the equations are similar for both, as you can see from the formulas. For either NPPI or CCS, we do sum over trajectories by weighting deviation from this desired yaw angle. So for both losses, we just integrated this penalty term by using pure pursuits and Stanley controls yaw angle cost derivations. These cost modifications will be tested afterwards, implementing car dynamics testing with an original approach.
So for a quick recap, the paper's experiment used a double integrator, but we are focusing on a vehicle dynamics called bicycle model. So bicycle model approximates the car as having two wheels, front wheel for steering and rear wheel for propulsion. Wheelbase L is the distance between the car's front and the rear axles, and we set it to 0.1 meter for our implementation. So for simulating the system, we need to predict the future state of a car given its current state and the control inputs. As a current state, we give positions of x and y, heading angle theta, and velocity. And the control inputs are acceleration and steering angle delta. Given these, we get an output of the state derivatives. But the issue we are facing now is that this car dynamic will not work with CCS MPPI. As you can see in the left, it works well in regular MPPI. This is not the case for CCS MPPI because it assumes a linear dynamics. On the other hand, our bicycle model introduces nonlinearities due to steering dynamics and state dependencies like velocity. Our current plan is to use Jacobian-based linearization. We linearize the system around specific operating points, producing state space representations A and B. This means that we will linearize in current state each time, and this way it will work not only for when the theta is 0. So we are going well as we have planned, and here is our future plan. Currently, we are in the progress with making CCS and PPI work in the bicycle model, and we are progressing about 50% for pure pursuit and Stanley control. And the detailed plan for the coming weeks are finalizing the tracks where all the approaches will be evaluated, integrating costs from Stanley and per pursuit control in MPPI or CCS, and then run the bicycle model with proper linearization in the CCS algorithm, and run our algorithm and the original one in the same environment and compare the results. Thank you for listening.